Um in this problem, this follows the previous problem where we talked about the point of continuity of a function being a g delta. Here, what we are going to have is something else. It's a collection or a sequence of continuous functions. So we have the fn's, okay, which are defined on R, which are continuous for every n, okay. And what we want to show is that the set where uh, the set where so let's call it C, okay, for convergence, x such that limit of fn of x where n goes to infinity exists. So this set is an intersection, a countable intersection of f sigma sets. Okay? So note that if it's empty, the result is obvious. Okay? So because it's going to be closed basically. Okay? So it's obvious. But so we assume that C is not empty. Okay? So here the trick is to see that a sequence is convergent in R if and only if it is Cauchy. Therefore, C is just x such that the sequence fn of x is Cauchy, which allows us to work with this without having to specify the limit. It's very, very beautiful. Okay, so completeness here of R plays a major role. Okay, so what does it mean to be Cauchy? This means that for every epsilon, there exists n epsilon such that for every n and m greater than n epsilon, we have fn of x minus fm of x less than epsilon. So this is very important because this will allow us now to introduce the following set: a, n, m, epsilon to be the set of x such that, okay, fn of x minus fm of x is less than epsilon, okay, or equal. So since fn and fm are continuous, therefore absolute value of fn minus fm is continuous, therefore the set a, n, m, epsilon is closed. Okay? So now what does it mean that x belongs to C? This means that sequence is Cauchy, which means that x for every epsilon, so x will belong to, okay, a, n, m, epsilon for, no, let's write it this way. For every epsilon, if and only if, for every epsilon there exists n such that x belongs to the intersection of all a, n, m, epsilon, where n and m are greater than n. So this set here, this set is closed because it's an intersection of closed sets. Okay? So now if we take now the intersection, so this will tell us what? That x belongs to C if and only if x belongs to the union, okay? No, first the intersection for every epsilon. So it's going to be the intersection over epsilon, right? And then since we have there exists an n, so it's going to be the union over n, okay? And then the intersection of all a, n, m, epsilon, where n and m are greater than capital N. So as you can see, this one is closed, and since this is countable, this one here will be uh, an F sigma. So this is an F sigma for sure, because it's a union, a countable union of closed sets, so it's an F sigma. Okay. Now, to finish the job, is that it's enough to show, in fact, that this is the same as the intersection. X belongs to the intersection, and instead of taking epsilon, we'll take k greater or equal than 1, and then we take the union n greater than 1, intersection n and m greater than n, and now we take a, n, m, and 1 over k. So by doing this, using the properties of the real line, then C is exactly this set, and now we have what? The final trick is that this will be what? A countable intersection of F sigma as claimed.